Welcome to this demonstration for ANSYS Composite Prep Post by CAE Associates. I'm George Bauer. This demonstration is intending to present to you the basic features of ANSYS Composite Prep Post software operation. The goal is to get you started with ACP functionality for pre- and post-processing your composite finite element models. We'll start our demonstration today with a T section, an example structural problem, and review ACP features from start to finish throughout the analysis. Today I'm showing in Workbench Mechanical an example problem that created some geometry, created a mesh, and applied some loads and boundary conditions. When you install ANSYS Composite Prep Post, you have the option to operate ACP through Workbench or as a standalone software product. In this case, I've set the example problem up with, imagine a T-section that's a composite laminate buildup on a skin with a core. This example problem will highlight some of the features of setting up composite properties and laminates in ACP and run through an example from start to finish. In this case here, I've set up the model with an example mesh, and these are shell elements, and we'll go through this example with shell elements. And as we can see here from our static structural folder, we have applied loads and a fixed boundary condition. From within Mechanical, if you highlight the static structural folder, you can go up to the top menu and launch ACP from within Mechanical. ACP can also be operated from a standalone procedure and essentially working with ANSYS Mechanical APDL CDB files or archive files. So you can also launch ACP from the ANSYS Workbench or from the Windows Start menu in the ANSYS 12.1 folder under ACP, and the version we're using is 12.1.5 today. So let me launch ACP as a standalone operation, and then from here, to demonstrate the import feature, we can go to the File and Import Preprocessing Model. From here, we define our CDB file as a tstiffener.cdb that was created from ANSYS Mechanical APDL, and let's import that. As this imports, we'll be importing both loads, boundary conditions, nodes, and shell elements. We'll see that importing the loads and boundary conditions can be utilized for our subsequent ANSYS analysis and then our post-processing within ACP. After we import our model here, I'd like to just review the overall layout of ACP, the structure of the windows and menus and icons. You can see here, this has a familiar look and feel in regards to essentially the outline tree and different folders and subfolders within the outline tree. This is very familiar to our Workbench Mechanical. Up on the top here, we have a few basic menus for file and saving and importing and tools and preferences. The main window here is identified as Scene 1. This essentially controls our main graphics window for this particular scene. ACP identifies this object as a scene, and you can create multiple tabs or multiple scenes for model pre- and post-processing. Up in the top, we also have some visual icons. We have the standard orthogonal view icons here, and you can see we can switch our view from our model for these orthogonal views. And with our mouse functionality being very similar to Workbench, we can use the middle mouse button to essentially do the global rotate, and essentially rotate our model around for viewing. The right mouse button can also be used for zooming in. This gives you the rubber band box zoom, very similar to Mechanical. And with the icon up at the top left here, we have a zoom to fit window. Should you zoom in too far, we can always, or zoom in for a particular reason, we can always zoom out to fit the entire model. So these are our first few sets of icons here, our main graphics window, We also have a few tabs down below that logs our commands and logs the Python scripting that drives ACP. This also up at the top, a couple more viewing controls that I'd like to review is the perspective view. This particular icon toggles projection, and this is just a method of using an orthogonal view similar to mechanical and a perspective view. Today I'll go through the demonstration with the orthogonal view. Once we get our model in a position and display that we like, we can also use the particular feature called views, and we can capture the view, and this view will show up in the outline tree down below. Should we move into a different view, have different items displayed, we can always go back to that saved view just by clicking the view in the outline tree. Next to the right is a camera icon that allows you to save a hard copy image to your hard disk of what is being displayed. And the next two icons to the right are toggle switches for displaying element edges in a shaded surface. So these act like toggles to allow you just to show the shell element connectivity or just a shaded image. So these are our basic viewing options and mouse controls just to navigate through the model. The rest of these icons up at top we'll cover as we get through setting up our problem. Looking at our left here, our outline tree, the major categories of the folders are set up in a manner that is consistent with setting up a problem and analyzing a structural problem. So on the left, our first category here is material data. We'll set up material names, our engineering constants. We'll set up fabrics such as materials and thicknesses, and we can also collect stackups and sublaminage, which allows for essentially a hierarchical list of organizing our materials, creating collections of materials to then go to our model and apply in the distinct zones or regions. So that's our material data. Our element sets are essentially collections or sets of elements. We could see from our import of the CDB file, we do have a few elements sets here that are predefined. I'll explain those and how we can work with those shortly. Then we have edge sets, and then we'll go through this in a sequence in setting up our problem. For material data, let's first look at defining materials. You can see as we imported our CDB file, there are a couple of materials that were imported with the model. If we double-click on these items in the outline tree, that essentially brings up the material properties or brings up the properties of any entity you double-click on. You can see there's various tabs on the material properties. This particular material properties here were imported with the model. They are an example homogeneous material, and we won't need these for this particular problem, so I'm going to go ahead and delete these. You'll see if you right-click over each item in the outline tree, you have the ability to create materials. Essentially right-clicking over various options in the outline tree gives you the different operations you can perform with that specific item. Under materials, let's go ahead and create material properties for the different fabrics and unidirectional fabrics and cores we'll be utilizing in this example. For our first material, I'd like to create a unidirectional material. We'll call this, essentially we'll call this material. First we'll give it a name, and we'll say this is carbon uni for a unidirectional tape example material. Here we see that I mentioned the tabs previously. Here we define the engineering constants that will be used in the finite element formulation. And we also have some additional tabs here, such as strain limits, stress limits, Puck constants, and CTE coefficients. These are just different information used for solving the problem in engineering constants and thermal expansion coefficients should it be a thermal structural problem. These three tabs here allow you to define material allowables, such as strain limits for post-processing, comparing results, and defining failure conditions and failure post-processing. For this carbon unidirectional material, let's first enter an example density. Today's problem, I'll be working in English units, and for density, we want to stay consistent in using mass density, so 1.7 e to the minus 4. And you'll see the various orthotropic engineering constants required for our particular composite properties. So in the one direction, RU1, typical carbon unidirectional tape, for example, will have 2.2 e to the 7 modulus in psi, and through the off axis we have 1.3 e to the 6, 1.3 e to the 6. This allows the engineering notation. Let's go ahead and enter in our Poisson's ratio. So we have 0.32, 0.32 matrix dominated Poisson's ratio, and the off axis 0.45. Let's also enter our orthotropic shear modulus for G12. Again, these are just example numbers, and you can enter material information from your data for any engineering database or control database that you may have at your company. There's 7.7 e to the 5 psi and 4.3 e to the 5. We also define the ply type here as a unidirectional tape, unidirectional regular ply type. Okay, so let's hit OK. You'll see our outline tree is updated. There's a little yellow lightning bolt next to this item in the outline tree, and this is similar to the design modeler, essentially, and mechanical items. In the significance of the yellow lightning bolt indicates you should process or update outline tree so that the ACP can fully process all options within the outline tree. In this case, we can update with a right click to process that unidirectional material, or if we have multiple items that need processing, we can click on the upper right icon to update the entire tree. Okay, I'd like to use a couple other materials for this example problem, and to save time rather than entering information for a fabric and a core, if you right-click over material, you can import materials from a CSV file. So I've created some materials. I exported them previously from ACP, and I'd like to import these materials back in. This is a nice way to essentially save time, create consistency in entering your material properties. So here you can see I have a unidirectional tape. If I open up a fabric, there's a woven ply type for a carbon fabric and a core material. So this is identified specifically as a honeycomb core. And then you can obviously enter the appropriate stress and strain limits for post-processing. After we're done with defining the material, essentially engineering constants, we create what we call fabrics, or essentially defined plies. And these plies can be unidirectional plies, they can be woven fabrics, and they can be core, but they're essentially the nomenclature within ACP is identified as fabrics. So let's go ahead and create a fabric for each one of our materials we'll be using in our laminate Stackup. Let's go ahead and create a fabric here. Our first fabric will be our carbon unidirectional fabric, carbon uni, and in this case we'll just identify the material as our unidirectional tape material, and this is where we enter the thickness. So we have 0.005, 5/1000ths of an inch thickness for each ply of our tape. In this information we can also enter our costing information for price per unit area and draping coefficients for draping simulations. We'll touch on draping a little bit later, but in this introductory presentation we won't go into draping too much and other advanced functionalities. Let's figure on a basic setup here with a unidirectional fabric. Also, let's create another fabric for, we'll assign our carbon. This will be our carbon fabric material, and this will be slightly thicker as 7.5/1000ths. And finally, let's create a fabric for our core. And this will be assigned the core material, and we'll have a 1/4 inch core in the skin. Okay, we have yellow lightning bolts. Let's fully process or update our outline tree. Next we have, within the material data category, we have stackups and sublaminates. This allows you to define essentially a hierarchical list of combinations of fabrics and perhaps groups of stackups and sublaminates. And in an example, I'd like to use a stackup in this particular problem for the flat skin here. Imagine a T that we have the T blade here, we have two legs of the T, and also we have an overall large or gross area skin. In the skin, I would like to build up a honeycomb core with face sheets and then the solid laminate T on top of that. So let's go ahead and generate a stackup which we can use with construction for our T angles. Essentially, we're going to build an L on one side, an L on the other to comprise the entire T solid laminate, and our skin will include a core. So let's go ahead and generate a stackup. Now, a stackup you can envision as some companies offer a pre-built sequence of tape or fabric stacking sequence that is essentially pre-manufactured or grouped together. In this example, I'm going to put in a stackup here called Stackup Book 1, and I'm going to generate essentially a pre-built 6-layer stackup where I can utilize for applies across the model in various regions. So this allows you to kind of build a stackup that allows you to quickly apply this to different regions of your model. In this new window here, we can essentially build the stackup with symmetry or without symmetry. We can define a stacking sequence as top-down or bottom-up, and essentially build a small spreadsheet of plies in various angles. So in this case, I'm going to build my Book 1 as a sequence of unidirectional tape, as if we purchased a single book to apply to our T section, and we can build this like a small spreadsheet with a number of unidirectional plies at various angles. I'll create a quick 6-ply book here, and then we can utilize this throughout our model. Let's go with a 0. Let's make this a symmetric stacking sequence. We'll make this minus 45, and the last one we'll make as 90. Again, you can see our costing and draping coefficients in this particular stackup. Let me correct that. That should be a 45. Okay. So okay, let's go ahead and update this. You'll see that in our stacking sequence, when we apply or create our ply groups, we can use both fabrics and stackups to combine to build our final laminate. Next, let's take a look at what's next in our outline tree in as much as element sets. These particular sets are groups of elements where we can envision these as essentially regions where we will apply our ply groups. These element sets come in from either mechanical or mechanical APDL as named selections or named components. Now, these are essentially, you can see the lock symbol here. These are kind of imported with the CDB file or imported from mechanical, and you cannot change these. If you want particular groups of elements, you can create additional element sets. I created name selections with the geometry in mechanical, and this makes the ply definition and assignment pretty easy. And we can see these are pre-built for the skin, covers the entire section, and the two sides of this particular T as being useful for defining the two L sections. I'm going to briefly mention edge sets, CAD geometries, and rules. Rules we'll touch on towards the end as a method of looking at regions for ply drop-offs and regions for ply boundaries. And these allow us, essentially when we assign plies to specific element sets and oriented element sets, this allows us to have additional control of where those ply boundaries stop. So I'll give an example of rules. Some advanced features include edge sets and CAD geometries. We won't cover those now, but essentially these give additional functionality for defining CAD geometries for machine core, many operations with the 3D shell element extrusion into composite solid geometry for ply cutoffs, mold-to-mold kind of 3D extrusion modeling, ply essentially post-cure cutting operations. So this gives you a lot of functionality for 3D extrusion, both with CAD geometries and edge sets. You can use CAD geometries for core materials, and that you can still use with shell geometry. We'll cover that in an advanced feature demo. Let's take a look now in our rosettes category. These are essentially coordinate systems, and you can see the lock symbol here. These are coordinate systems defined from our mechanical APDL. So coordinate system 15 was defined previously, and this is I'll be using for our fiber orientation direction. 12 and 13 were also defined, but with the various items in the outline tree, if you right-click over those, we can hide and show various components, element sets, and so forth. And this acts like as a hide and show option to display or not display throughout model building and post-processing. So let me hide two of these rosettes and keep rosette 15 here as we'll kind of coordinate our ply orientation direction. We can also create rosettes here if we did not import rosettes, you can create new ones. Let's move on now to oriented element sets. Oriented element sets are essentially the core definition of how we will apply our ply stackup to the element sets and define the reference direction and reference orientation. So this is an important part of defining the composite layout. Let's start off by describing this by creating an oriented element set for our skin. Taking a look at this menu, we have a couple key components I'll cover here. And let's first define an oriented element set for our skin. What this does is combines element sets or groups of elements, in this case the skin element, and in this box here we define the normal orientation, essentially the definition from the mold surface or the bottom and the direction normal. So let's define our normal orientation of the skin as extruding downwards. We're going to have a T-section on top of the skin, and we'll have the skin extruding downwards. So in this case, we have an orientation point, and this is shown as a preview in this direction. This orientation direction corresponds to the global XYZ axis in this particular option, and I'd like this to be oriented in the -Y, in the -1 direction. I want the normal direction pointing down. Here you can preview this direction with the purple arrow. The rosette defines the 0-degree axis from the x-axis of the rosette you specify. So we click in this box here, we specify rosette number 15, this gets highlighted. This will be the 0-degree material orientation definition for the elements within skin, and this fully defines the element-oriented set. Some additional features here are rule selection and draping, and again, those are some advanced features. Let's hit OK here, and we'll see the yellow lightning bolt. Let's update that, and we'll see the element-oriented set. A couple of things to check. We're going to assign this to ply definition, so a couple of things to check now are the orientation of the reference system. We highlight our blue icon here. The blue icon shows the basic shell element normal definition. This is coming in from the shell connectivity. If we turn that off and take a look at our definition for ply stacking sequence, this is our normal orientation. And this, you could see, if we zoom in, that our normal orientation from the skin is downward. So this gives you some flexibility for constructing the laminate in the direction that you need to for your particular part. Let me turn off that information and then turn on the next toggle for the reference direction. So this will define the 0-degree axis. Let me back up a little bit. The 0-degree axis for the ply definition. You can see all the arrows are pointing in the correct direction. We'll specify apply stacking sequence angle theta with respect to this reference direction. All right, let me turn off that toggle. We have a couple more oriented element sets to define before we define our apply stacking sequence. See, this is highlighted in green. Let's go ahead and define the next oriented element set. Okay, for this oriented set, let's go ahead and define this as T side 1. So this will be the closest side of the T definition. For our element set, we'll select this group of elements. In the orientation point, in this case, we'd like the normals to point in the X direction here. Let's take a look what we need to define here as the orientation direction. We'd like this in the positive global X, positive global Y. On this face, it'll align with the X-axis. On this face, it'll align with the positive Y. Let's create this as a 1, 1, 0 orientation. Now this, again, is projected on the element face for the normal direction to align with. The rosette, let's stay consistent with rosette number 15 as the X direction for our angle definition. So this fully defines T side 1. And let's do the same with the next oriented element set. That will be the opposite side of our T blade. This will be T side 2. We use element set T side 2. For this orientation, let's use a -1 direction, +1, and the rosettes, we use the same consistent X-axis orientation. Let's bring this into view, and before we view further, let's update our model as well as review our reference directions. Here we could see 4 oriented element set T side 2. Here's our direction normal. On the upright face, it's upwards. On the skin side, it's upwards, and the upright, it's oriented to the left. And likewise, if we highlight the other, we have the proper normal direction. And with both, we also have the X direction in the proper direction as well. All right, with our oriented element sets fully defined, our next step is to define our modeling ply groups. So let's go back and now define our plies, the regions, the zones of our plies and their applications and stacking sequence. For modeling ply groups, if we right-click, we can create a ply group. We'll construct this in a skin stiffener option with both sides of the L-sided stiffener. Let's create our first ply group as the skin ply group. So first we define the skin. Once we create the group, this is kind of a subcategory. We can now create the plies from our fabrics and stackups and sublaminates if you have them. Let's create our skin first. First ply for our skin, we have a modeling ply. We have the oriented element sets we just defined. The global ply numbering is automatically incremented, and we can define our skin. We're going to have two ply face sheets on our skin as well as a core center. So let's first define our carbon fabric as a face sheet with a ply angle of 45 degrees. We'll have one layer. This is not the core option, so we'll leave that alone. Let's hit OK, and we can see how we can start building our skin definition. This is modeling ply 1. Once you have a ply that's defined for this group, we have the option to copy and paste to arrange multiple plies. This comes in handy for defining your stacking sequence. So let me copy this and paste that after. Let's double check modeling ply 2. Perhaps this would be a -45 ply, one layer. Let's hit OK here. Let's toggle off the arrows. This is getting our visualization kind of busy here. Let's go ahead and paste another ply. This will be the center of our skin. This will be a 0-degree ply, not of the carbon fabric, but of our core material. And let's see, it automatically incremented our global ply index. So here we hit OK. Let's go ahead and copy this -45 as bounding on the other side of our core, and the 45-degree on the final outside face. Now, once we have these plies, we want to kind of visualize or double check our stacking sequence. Let's go ahead and update this. Let's do a global update of each of these plies. And we can see by clicking on each modeling ply within this ply group, we have the color contour of the angle defined. We can see the 45 range is in the green. We have a 45, a -45, the core at 0. We have a -45 and a 45. So this helps us visually update or verify the stacking sequence. Let me go ahead and save this model. Save this ACP database. Let's go ahead and save this as a collection of our data. Now, with the modeling ply groups, you notice I right-click to create this group and start building up the ply definition with respect to the oriented element sets. You can also import and export from a CSV file. So what I've done previously was to kind of speed up the ply definition in our various regions. I built a T-stiffener model. I exported that. So let me import that CSV file now. You have the option to import to add all those to our modeling ply groups. We can delete the existing. We can delete any existing definition of ply groups. Let me go ahead and update this. Import that. So this allows you to quickly, or allows you to save definitions that you've already used for model building, and instead of typing in and building the laminates all over again, allows you to save via import and via export and import into various other models. So we can look at these. We have just to double check our T-side definition. We have modeling ply here. In this definition, we used some unidirectional tape in the T-stiffener on both sides, but also for the modeling plies, we used our Stackup, our book Stackup. So each modeling ply here is identified as a single modeling ply, but we know from our stacking sequence this is actually 6 individual plies. So once we generate or update this, we'll see that if we expand each one of these modeling plies, it's actually a whole section of the 6 plies in the analysis plies. So that's kind of the hierarchical nature for modeling plies and analysis plies for the definition. When the model is going to be solved, essentially the root definition of all analysis plies will be defined as the section definition for the shell structure. So we can view here the different angles based in the different groups, so we can verify that. The next thing I'd like to highlight as a verification tool for pre-processing is the section cuts. Section cuts gives you a very handy way to essentially do a cut in various orientations and placement in your model to verify the stacking sequence. So this is a strong tool to verify within the various regions, ply groups, and stacking sequence the exact definition. So let me go ahead and under our section cuts, let's go ahead, right-click, and create a section cut. This brings up a separate menu and a tool that allows you to place and define the orientation of our section cut through our model to visualize the ply stacking sequence. In this case, it automatically defined kind of the global centroid of our model. We can grab the arrow to orient the section cut or orient the position. If we do that, this defines the center. We can also define this specifically orientation with, for example, a discrete 0, 0, 1 vector definition. so we take an orthogonal section cut through our model. We have a core scale factor. Let's keep that. We have a 1/4 inch core, which should visualize okay. Let's keep the core scale factor at 1.0. And then we have a ply scale factor. Let's bump up to visualize the thin plies a little bit more. Let's bump that up to 3, scale factor of 3. So let's call this section cut 1, and we hit OK. We now have an item in our outline tree defined as section cut 1. Once we update that, you can see visualizing through our model, it defines, kind of gives us both the ply angle for each individual ply and the stacking sequence of all plies for all modeling ply groups. So this allows us to verify the kind of the final composition of the laminate definition. Let's turn off a couple of visualizations. Let's turn off the shaded surface and the element edges so we can zoom in here to verify our stacking sequence. So here we can see we have, for the section cut, we have the 2 skin plies. We have a core ply that's fairly thicker, and then we can see our L, our angle definition. Okay. And let's back up. Let's zoom out a little bit here. As we can see, the skin definition goes over quite a bit further here, and that extends beyond the edge of the T. And that's our basic 2-ply definition with the core. All right, let's zoom out a moment. That is our section cut tool. Let's go ahead and turn back on our element edges and our element shading. So that's basically a number of the pre-processing tools to build up the plies, build up the pre-processing portion of the model. The next section of this demonstration is to review how to solve the problem and then continue on to post-process. In our outline tree down below, we have in our solutions folder, if we right-click, we have options to save the current analysis model. This allows us to save a CDB file of the problem. We can solve the model while within ACP, so we don't have to exit out of ACP. And then we can import results, or create an envelope solution of multiple results. So let's go ahead and bring up the properties. We can double-click on solutions or right-click on solutions. This gives you a little information window as well as the output file that will be generated once we solve. So we can right-click under Solution. We have our loads and boundary conditions defined through the CDB file. So let's go ahead and solve the current model. You can see in the background it's launching the ANSYS job that takes the composite shell definition and section definition and solves the problem. The output file is echoed in this text window here, and we can see this is the standard output from the ANSYS solver. If we scroll down below, we can find that the ANSYS run has completed with no error messages. So let's go ahead and import those results to start post-processing. To do that, we right-click over Solution again and import results. We're essentially going to create an item in the outline tree. Let's say for this particular solution, we only had one load case. We'll call this solution limit load case. The format will read the ANSYS RST file, binary file directly for the element information. So let's define the path to that RST file. It's the default directory we saved in, and this will essentially read the strains and stresses from the file. It recognizes there's one time step. Once we hit OK, that identifies this as a solution that we can read information from, so we can update that and read those results into ACP. Now, to post-process this, we essentially want to create different scenes or different graphics windows to post-process various quantities that we're interested in, whether it's displacements or stresses or strains. So to do that, we can first define what types of results quantities we're interested in through the definitions folder. With the definitions folder, you can see angle is already existing. That's ply angle. We've done some pre-processing with color contours for ply angles. Through definitions, we can define what other post-processing quantities we'd like to review. So here, right-clicking over there, we're allowed to insert a deformation post-processing quantity. Call that deformation 1 for an item such as strains and failure criteria. For failure criteria, there's additional information we can specify. For example, max strain, say max strain for our limit case. We'll define this as a definition, and we can configure various failure criteria based on the information we've supplied. So we can define fiber failure, matrix factor failure, and work on different weighting factors. So there's a large variety of ways to post-process information based on different criteria from your particular materials you're using. So in here, we defined a max strain. Let's hit OK. And these are basic definitions. To link these results quantities to our solution, you go ahead and create a new scene, a new post-processing window. So let's go ahead and right-click and create a new scene. This essentially generates a new tab, a new graphics window. This is identified as Scene 2. What I like to do is just hit OK here in this new tab, and kind of with our display, we have some of the graphics here that's left over from our pre-processing. So let me hide all of our rosettes so we can post-process this. We've also, with our section cuts, we can hide those and just get down to the basic information for Scene 2, in which we want to post-process the basic model. We can always go back to the scene definition. If we double-click or right-click and hit Properties, we can now define what type of information we'd like to post-process in this graphic Scene 2. Let's go ahead and identify the source of the results, and that's our RST file linked to the limit load case. For input, let's go look at our information on a deformed, essentially a deformed shape plot, and show the undeformed mesh. Now, there's three kind of major categories here for the deformation, for color contours being plotted on the model, vector definition for vector plots, and the failure mode plot. So this gives a lot of flexibility on items to post-process. In this case, if we just identify a deformed shape with a scale factor, let's magnify the deformation so we can visualize them. We can also show the undeformed mesh. If we hit Apply, let's go ahead and takes a look at our deformation, nodal deformation information, and we can post-process this deformed shape. So the stiffener here is stiffening up the structure over in this region. Again, this is kind of misleading. We are scaling the results. For contours, if we're interested in magnitude, we can go from our deformation definition and plot the nodal displacements, either an x component or the root sum squared u sum. Once we define contour, we can hit Apply and then show the contours. Let's go ahead and do not show the undeformed mesh to clean this up a little bit. Now we have u sum deformation. Out here in the free edge, we have much higher deformation than in the stiffened region. So, utilizing the scene properties here, we can also identify the different types of results quantities to post-process. We can include failure mode plots. So this is kind of how we control what is being post-processed in this particular window and from the various quantities you're interested in. So that's a brief introduction to pre- and post-processing of the composite prep post software. A couple other additional things couple advanced features I'd like to show you now. Let me hit OK here. Also, let's switch back to our initial model building scene here. Let me go back and say, let's show a couple additional things with respect to building solid models to get you started with that, and rule definition. Let me delete this solution, as we're going to be generating a new model with including new ply definition in describing our new model. For solid models, this allows you to take an existing ply definition and mesh definition and extrude that in a various number of ways. This is a very powerful feature for extruding shell and ply definition into solid finite elements and layered solids, essentially. Let me get you started with just showing you in this example how to generate a solid model. Let's go ahead and shut off our section cut information. Let's hide that and also hide our rosette. In our solid models category, if we right-click and create solid model, this gives us various options to extrude the element definition in how to create the solid elements. Let's first select for our solid model properties. Now, let's go ahead and look at extrusion methods. Well, first, let's select the element sets. Let's go ahead and extrude all the elements to review how we can extrude all these elements all at once. And let's look at the extrusion method. The extrusion method allows you to extrude and create solid elements for each and every analysis ply. You can create a solid finite element definition with a layered solid element and the shell section definition using monolithic. You can extrude it material-wise or modeling ply-wise. There's also some other options here for extrusion, some advanced features here for extruding those shell elements. Let's keep this to analysis ply-wise and keep the offset direction, extruding each shell in the shell element normal. If we hit OK here, just this basic definition, you can see there's extrusion guides and snap to geometry, advanced features. If we keep this basic definition here, let's update our model here and review how this can be extruded. It goes through all the elements, essentially does the core sample in defining all the analysis plies we're extruding with, and creates the solid elements. Now let me go ahead and zoom in our solid finite element here just to show you some of the definition. We note that here is our skin with the two 7,500 ply thicknesses, our quarter-inch core, and there's the outside skin. We defined our bottom to top direction as lower. That extruded it in this direction. So our shells are actually on this layer. The back-to-back L sections complete this T-stiffener and extruded solid elements in this direction here. The other thing I'd like to show you in this is we had the T stopping at a specific section along our skin. If we zoom in here, the extrusion method knows the ply boundaries and it can taper off the ply boundaries once that ply has stopped. We have the option when we export this model to include those ply drops or not include, depending on the application you'd like to analyze. So this is, at a very minimum, is the basic solid model definition. Let me hide that and show you another feature. Next, I'd like to show you is the ply draping capability. With our ply draping, notice when we were creating our modeling ply groups, we can specify draping on an individual ply. We can also specify draping with an oriented element set. Performing the draping with an oriented element set allows you to essentially define any ply being applied with the oriented element set to be draped over that specific surface. So it performs the draping simulation to calculate those ply angles. In this case, let me just show a simple example of draping on this particular T section and look at the resultant angles of the draping simulation. For modeling ply 8 on T side 1, if we review the properties of this particular ply, its basic definition is the material for this Stackup. Actually, let me use a single instead of the ply book. Let me use the ply, a single fabric ply here, or single unidirectional ply. Let's look at the properties here. So for here, we have the single ply, it's carbon unidirectional tape with a ply angle of 0. We can select rules. We can also taper edges. That would be more appropriate for core. In this case, we want to toggle on the draping simulation. With this, there's some definitions here. By default, it has a seed point and an automatic draping definition based on the elements included within this group. Let's change the seed point and define the direction of draping. Let's go ahead and select an element here to start as the draping origin. Let's zoom back out and then define the direction, just as an example in the, let's go ahead here in the, let's go with the -1 in the x direction and -1 in the z. -1 here, our triad is getting updated as we type this in. Let's just show a draping starting it from this corner and draping over this angle. Let's hit OK. And let's go ahead and update. So it goes through a draping simulation, and after the one way we can review the draping simulation results is looking at the resultant ply angles. Normally we check the orientation definition through our fiber direction toggle switch. In this case, the blue arrow shows draped fiber directions. So if we zoom in here, we can look at how the angle direction starts from our corner based on our definition, and then the draping simulation shows some scissoring in where the contour of this upright angle is kind of contoured up. So there is some change in ply angle based on our ply definition, our draping coefficients in this particular orientation. If this is one way we can review the results of different orientation, different draping definition, if we were to go back in this modeling ply and define, instead of a direction for draping at an angle, let's just go ahead and change this back to a draping angle oriented in this x-axis we've defined. Well, we can see now, if we update this, the resultant or the effect of changing the direction of draping that ply on this particular orientation. So we can see these arrows now get updated a little bit more in the orientation we were expecting. So that's one way to perform the draping simulation for draping over your particular geometry. Okay, the last thing I'd like to show you in this demonstration is the availability of using rules for defining ply boundaries that may be different than the element groups you've specified. So this allows you to define other method of defining ply drop-off regions and so forth, other than using specific element boundaries. So let's back up here. Let's toggle off some of our information. Let's zoom out again. I'd like to first go up to our rules folder or category here and create a parallel rule. There's various rules to utilize, both with shell section definition, solid model extrusion, and so forth. I'm just going to demonstrate the method of a simple parallel rule. Let's create a parallel rule and say, let's say, for example, one of our skin plies is initially defined over the entire region, but would like to cut that off or drop that off at a specific geometric point. There's various rules you can utilize, from edge rules to parallel rules, cylindrical rules. Let me just define a simple parallel rule. In this case, we have an origin and a direction. The triad allows you to preview the definition. The lower and limit, essentially this works like an include rule. Any elements within this parallel region will include the ply in its definition. For lower limit, let's change this to a -5, and for an upper limit, let's change this to 5. So 5 inches behind and forward of this origin, we're going to include that in our ply definition. If we apply, we get a preview, essentially -5 and +5. We can now look at how this rule will control our ply boundaries. So this can certainly stop or start within element regions or definitions. So let's call this parallel rule for skin 1. Okay, with that now being established and we have our model updated, let's go to our skin. With this particular skin ply here, let's go take a look at our properties. For this modeling ply property, we can select rules to apply for this specific this modeling ply. So let's go ahead and select rule. We can use this spreadsheet to use the parallel skin rule we just defined. We can hit OK here. And now with this as part of the definition of the modeling ply properties, let's go ahead and hit OK. And now let's go ahead and update this particular ply. With this ply being highlighted, we can see which elements were selected within this region. So that's helpful in determining the effect of the ply. What's also helpful is going back to our section cut. Let's update our section cut and review. Okay, with this process, let's go ahead and hide our element shaded image and zoom in the region with our plies. It might be a little bit hard to see here. So with this, you can see that lower skin ply definition was cut off right at this region. So this, essentially this 45-degree ply, we can visually see now is cut off. Just backing up a little bit, you can see this is the edge of the T. We define the region where to cut that ply off with this specific rule at this location. We have the solid model still defined in this particular database. So let's go ahead and update the solid model to review the ply rule and the ply cutoff again in this capacity. Let me zoom back out a bit just to give us a perspective. Let's turn on our elements. And we also have to, right now the solid model is hidden, so let's go ahead and show that. So if we look in, you can see here is our basic solid model. Let's go ahead and zoom in the same region where we expect that ply to drop off with our rule. These face sheets are rather thin, but we can see in this region where our rule cut that ply off, it now tapers that ply down in the region. Essentially, the rule cuts it off here and tapers that off. So this allows us, using rules, to define the shell section definition for analysis for different ply regions, as well as implement that in our solid model building. Okay. This concludes a brief overview of ANSYS ACP. There are many additional advanced features of ACP that I haven't shown here, but I hope this allows you to get started with composite modeling using ANSYS ACP, and I thank you for your time.